now I've got to analyze some triangles here to figure out exactly how to line up my trig relationships. So you're going to want to pay some relatively close attention to this because it can get a little bit confusing. This diagram can get a little bit busy, so you want to see what I'm drawing as I draw it. I'm going to think about this triangle right here. This is a right triangle because this vertical line here is exactly vertical because it's FG, it's gravity pointing straight down, and then the bottom line is the bottom of the ramp. It's like the bottom part of the ramp that's just resting straight horizontally on the floor. So this is a 90-degree angle down here in this corner. And if we remember our rules about a triangle, that all three angles must add up to 180 degrees. And the corollary of that, which is if it's a right triangle, the two angles that aren't the right angle have to add up to 90 degrees. That means that this angle up here in this corner is going to be 58 degrees, right? So let me erase all this busyness. No, that's not cooperating. Interesting. There we go. And label this up here 58 degrees. Okay. Now I'm going to consider this angle right here. That's a right angle because it's the angle between the x-axis and the y-axis. I mean, by definition, that's 90 degrees. And if this sliver of it on the left is 58 degrees, then the sliver of it on the right, which happily corresponds to the top angle of my vector triangle here, that has to be 32 degrees because the two of them must add up to 90. So it turns out, I'm going to erase this 58 so you don't get confused by it. It turns out that when you have an inclined plane kind of set up like this, that you can sort of skip straight to, oops, that's probably a little too big. If you have your inclined plane set up like this, you can kind of skip to the angle of your inclined plane is going to be this top angle in between your FG and your your FGY and your FG. It's going to have the same angle as the angle of the inclined plane. So now let's do some trig. If I look from the point of view of this 32-degree angle, if I take the sine of that, and I'm going to actually convert this, I'm going to change this back to theta. I'm going to get rid of the 32, I'm going to call it theta, so that when I'm done, we're going to have an equation that we can use with any angle, and then we'll plug theta back in, but more importantly, we'll just have this equation that we can, carry with us to the next problem that might have a different angle that's not 32. So, if I look at this angle here, sine theta is opposite over hypotenuse. Opposite the sine theta is FGX. And the hypotenuse of the triangle is the FG. So if I multiply both sides by FG, I get FG sine theta equals FGX. And hopefully we're comfortable enough with trig by now that you realize that if I were to stand at this corner and do the cosine, it's all going to be the exact same except it's going to be the adjacent angle, so that's going to give me FGY. So FGY is going to be equal to FG cosine theta. And so these are general equations. I'm going to put a box around them because they're important. And these are general equations that are essentially what you found. This was the conclusion to the pivot lab that we did with forces on the ramp. So hopefully you recognize these expressions from the free body diagram from that lab. Okay. Now, if I wanted to find these, it's pretty easy. I'm just going to go plugging in. I have one more piece of information that I know. Fg, we have an equation for that. The force of gravity is always the mass of the object times the acceleration due to gravity. So the next thing I'm going to do is actually replace Fg in these equations with mg. Now we have some general relationships here. Anytime we have a setup like this with something on an inclined plane, we can take the force of gravity and split it into FGY. We can find FGY. It's mg cosine theta of the angle of the incline. And we can find FGX. It's just going to be mg sine of the angle that makes up the incline. One final point that I'm going to make is that FGY and FGX replace FG. FG goes away. It doesn't matter anymore. It's done. It's over. We've replaced it with these two other things. It's kind of like, if I can make a little sort of algebra example over here for a second. It's like, imagine you had something that said 7x equals 4y plus, I don't know, a bunch of stuff. And for whatever reason, the algebra, you found that it might be easy to factor something or do your algebra. For whatever reason, it was convenient to take the 7x and split it into 3x plus 4x. You've replaced the 7x with the 3x plus the 4x. You wouldn't look at this algebraic equation and say, oh yeah, now on the left-hand side of the equal sign, I have 7x plus 3x plus 4x. Not what happened. You replaced the original thing with these two things that add up to it. That's what's happening here. So once you have split any force that's not along the axis, you've divided it into components that are along the axes, you just ignore the part that wasn't along that axis. You've replaced it with these other things, and the whole point of these other forces, I'll go back and move this one again, the whole purpose of this is that it lines up, well, that's not too bad of a drawing, lines up exactly along the axes. Now we can sum our forces in x and sum our forces in y, and go ahead and finish solving for anything that we need to know about this problem.